So today's episode is a very special podcast with two electrical engineers who work and have experience in the American utility industry. The goal of this podcast was to talk to professionals about the energy sector, and we covered traditional oil and coal energy sources, but also new emerging technologies of clean energy, whether that be solar power, wind energy, or even nuclear energy as well. The podcast is a bit long, so remember you can always check out the timestamps down below if there's a certain topic that you'd like to hear about. And just a small little promo. This is one of the great things about the Discord. We created a networking system on there so people of different professions can identify themselves, and you can actually talk to professionals about their industry and not just traders who are speculating on new technologies. So remember to check that out too in the link down below. I do want to say this is my second podcast ever. I'm still trying to improve as a podcaster and as an interviewer. If you have any suggestions, any feedback, please leave them in the comments down below. These two, they did great. They're professionals. They know their knowledge like the back of their hand. And me, I'm trying to keep the structure of the podcast, trying to keep the questions in order and the flow nice. But at times, this can be difficult because I'm still a newbie at this. So please be patient with me as I'm still trying to improve and learn on this journey. Without further ado, please show us some love, like the video, maybe subscribe to the channel, and I hope you enjoyed this conversation with Andrew and Brandon. The opinions expressed in this podcast are solely owned by the presenters and do not express the views or opinions of any past or current employer. Let's just kick this off, and if you guys just want to say some, what is your area of expertise in engineering? What is your background? If you just want to kick off with that, schooling or accomplishments or accolades, the Spark Notes version.
Go ahead, Brandon.
Okay, so I'm a substation design engineer, mainly on the physical equipment side, a little bit of PNC or protection and control experience. I am primarily in transmission in the power sector. Outside of that, went to school at UMSL-WashU Joint Engineering Program and have been working in consultants and the local utility in St. Louis. So a little bit of experience on both sides.
That's awesome.
Cool.
Yeah. And Andrew?
My background's pretty similar in terms of Brandon and I work together. I've been employed mainly at a company called Schweitzer Engineering Laboratories. It's a manufacturer of protective relays. My background is in protective relaying, protection and control, similar to Brandon. I did work at the same utility there for about a year, but I've been working at this company, SCL is shorthand for it, for the last almost 10 years, so quite a bit of time. So most of my background is in that protective relaying, substation design, things of that nature.
Awesome. Yeah, so sweet. It's awesome to have you both on here because I know for most people who are, when they're trying to look at information on this, they're often just finding economists or just traders who've like, oh, I read this article, that article, and it's way different when you hear from someone in the field or with a background or extra knowledge that they could provide. So, I mean, just hopping right into the first topic here. A big topic right now is how stable American infrastructure even is when it comes to electrical grids. In 2021, we all watched as the power went out in Texas. It caused major blackouts. And I know this was because of freezing gas pipelines, but what is the potentiality for this to happen again or for it to become, an even more severe issue that is, more widespread? Like if you could speak to that from your background and the field experience, if whoever wants to start. Brandon, if you want to kick in or.
Sure, I can kind of start off. So in my experience, on the utility side, I can kind of speak to a little bit from my understanding of all the factors that took place, because obviously it's not just one thing, it's kind of a domino effect where these types of things happen. It's usually not just one thing, because obviously the grid is built so that you have redundancy, so not one thing can just shut everything off. It's got to be kind of a chain reaction. So my understanding of that particular situation is obviously their equipment is not rated for such low temperatures, because obviously Texas is a southern state and it's usually pretty warm. So that my understanding, it's like a 100-year kind of winter storm that they get. So they don't size all of their equipment for that type of ruggedness. So when the temperature dropped well below what those pieces of equipment are, used to operating under, you had failures. So you had, like you said, freezing pipes, both for I think natural gas and and some of the equipment that's used for like the coal producing, the coal power plants, some of that equipment was failing. So when that happens, you have a loss of generation, but the demand for power, the load goes up. So in order to not destabilize the system or the grid, they have to shed load. So they have to literally turn things off. So blackouts or rolling blackouts. And so with all that kind of happening at once, you might say, well, aren't they connected to the whole grid? Couldn't they have just pulled in more power from other parts of the country that didn't have that issue? Well, unfortunately, ERCOT, or the Energy Reliability Council of Texas, they only have so many interconnects with the two other grids, the northern connection and the, Andrew, help me out. What are the two?
The Eastern Interconnect and the Western Interconnect.
The Western,
There's
yeah.
3 major grids in the U.S. Yep, correct.
Right. So there's only, I couldn't tell you how many exactly, but there's less than there could be. Let's put it that way. And I know Texas doesn't want to have as many, and I'm sure there's some, legalities that come with that for why that is. But I know FERC and NERC are looking at what happened to Texas and trying to figure out what they can do to kind of prevent that from happening again. But essentially, that's what happened. So you couldn't just have an endless supply of power coming from the Eastern Interconnect or the Western, because first off, there's only so many connection points, and then two, they're only rated for a certain amount of power and current capability. So when there's so much that's trying to be processed at once, if it's going to exceed the facility ratings, they're just going to trip it off. They're going to shed that load because they're not going to sacrifice that equipment for the power demand. So all those kind of things happen at once. So there's a few different pieces at play here, and I'm sure folks from Texas and other places might have some other insight of what I'm unaware of, but that's my current understanding.
Okay. That's interesting. So, Andrew, do you have anything you want to add before I?
Sure. There's some other aspects too. I'm like I said, a protective relaying guy, so that's kind of my background. Some interesting involvements that have happened over the years to increase reliability from especially a transmission perspective is in 2003. So it's been several years ago. There was a major blackout on the East Coast. So I know that's been quite a bit of time, but one of the biggest issues in that case wasn't necessarily failing equipment, but it was actually poor settings on some of these protective relays, some of the devices that I work with. And it actually caused a huge domino effect, a snowball into a lot of regulation. So actually now some of the major projects that I work on are regulatory type projects. So actually a lot of utilities now, especially transmission utilities, have to document how they're complying with some of these newer regulations and what we call PRC, which is like a protective relaying compliance type documentation. So FERC, the Federal Energy Regulatory Commission, that's the federal entity that actually kind of governs the electrical transmission grid in the U.S. or North America, basically Canada and the U.S. Because there's interconnects. And anywho, they essentially have ran several. They have several requirements that have been written out of that blackout. That was one of the major events that caused them to have all these regulations, and that's half the battle now is in ensuring that you're in compliance. Because if you're not, there's a lot of hefty fines for energy producers on the grid if they're proven to be uncompliant. So that's something that's been in the works for a long time, because a lot of these committees have developed these standards and these regulations. It's taken time for them to get voted in. It's not like one person wrote all these standards, but it's been very interesting from that perspective. If you're in this industry, that's one of the big things. And I know Brandon's been involved with it on the compliance side for, ratings. So ratings is in making sure your equipment can handle the amount of electricity flowing through it properly, so you don't cause any damage or there's safety issues and things of that nature. Those are some aspects that not everyone really is aware of unless you're in this industry, but it's definitely a big portion of it now today.
Yeah, just to give you an idea of those kinds of fines, some of them can be $1 million a day per situation. So if you have multiple substations that are not in compliance, each one's $1 million a day. So it's a very serious thing to be compliant and to report and to stay good with FERC and NERC. Which NERC is the North American Energy Reliability
Corporation.
Yeah, I always forget them, but we know who they are.
Yeah.
But they're more or less the underneath. So there's FERC, and then there's NERC, and then underneath that is your more local ones. So maybe like CERC, which is like the Southeastern Reliability Commission. Same thing. There's other ones as well
Okay.
around the U.S. But NERC is usually the one that we're most dealing with more than anything.
Yeah, FERC is kind of the government regulatory agent, and then they've hired NERC that kind of carries out all their, ensuring regulations are followed. But
So
FERC is the one that all the lawmakers and all the government officials that make the policies. Everything's technically run by FERC, but NERC is really the entity that kind of enforces all the standards.
okay. So they're a third party then? They're not actually a governmental body?
No, they're not. But
No.
I don't know
Okay.
all the I don't know all the details
Yeah.
with NERC and it's kind of an interesting. And I think NERC actually, I think they've existed for a long time. But again, after 2003, and a lot of these commissions and these standards, if you will, have really been written because of that, because it was a major problem. And you can actually read about it. There's all over the internet. If you look at, I think it was in like August or so, 2003, the Northeastern Blackout. It was a very big event. I forget how many millions of people were out of power for, like in New York City, for like dang near a week. So it was
Oh,
a
wow.
very big deal to get power back on. And I think it started somewhere up north in Canada. That was kind of the cascading failure that caused issues just as big, if not bigger than this latest Texas event.
Yeah. Yeah. Well, and even for the issues with the Texas event, I've heard that, if that even lasted longer than it had, it would have been, it escalates pretty rapidly when it goes down. Yeah. And it sounds like a lot of this is very intertwined, complex, slow, and expensive when you're making any changes as well. And I guess we'll kind of touch on a few other things, so I don't want to get too bogged down, but, kind of going over that regulation and all the different bodies involved when it comes to making any decisions. And I'd really like to set the pretense for this next question, that we all care about the environment. We want the environment, to be safe and for, future generations. So just separating, that and getting into the technicals. What is your opinion of the big governmental push and transitioning as we handle all these issues and try to strengthen the infrastructure and meet these compliances and update things to a changing environment? What do you think about the governmental push away from traditional oil and coal, just from the engineering perspective, as it pertains to sustainability and that structure, because it can be so catastrophic if that power goes down? Whoever would like to hop into that topic, because it's probably a lot to unload, but that's probably the big question everyone's asking right now.
Sure.
Yeah.
Well, in my experience, talking with different utility folks, power plant folks, green is good. It's not a bad thing by any means, but getting rid of coal, the biggest issue is being able to operate the system and having the reliability, right? Because sometimes the sun doesn't shine, the wind doesn't blow, and in some cases, if you have like a hydro dam, sometimes the water's not flowing very much because of evaporation issues of high temperatures, right? So there's always those limitations for renewable, which the solution for that issue is battery storage or some sort of energy storage, right? Which is still not come along as far as we'd like it to. It's on its way, but it's not 100% there yet. So having that reliability of coal, which is extremely cheap, 90% of the cost of coal is the transportation. It's not even the coal itself, right? And for a utility, the biggest thing is having the maintainability and reliability to keep the system just moving and not have these swings of like, oh, we got power now, but now we don't. We got the voltage, now we don't. And we wanted to have a balanced system, and that's really the biggest issue with renewable energy, is not having an easy way to balance it.
I guess that would also pertain to like what we were just talking about. The power goes out, you have to turn that equipment off. You don't want to overload it. If that's fluctuation constantly, it's causing even more issues to the delicate systems that need to continue to run. The kind of dig more into the battery and the technology not being there, how much do you think is just the innovation hasn't reached that point, and how much of that is related to like, well, we'd like to test this or that, but there's this guardrail and this red tape that we can't navigate to figure that out?
Sure.
Yeah.
I mean, in my opinion, from things that I've heard, the biggest issue is a lot of the manufacturers that you want to buy from don't end up staying around. So they'll just disappear in a few years. So
Hmm.
I know like I've heard of utilities buying like a big new battery bank, they install it, and the idea of what you when you buy equipment, you want it to last a given lifespan, right? You want to get your money out of it. So generally it's 15 years, 20 years, 30 years, depending on what it is. So ideally, when you shell out all this money for it, you want to make sure that you've got the ability, like, hey, if something goes wrong, I want to talk to the manufacturer about, hey, what did I do wrong? Can I get this new part? Can I, whatever, right? Because you want it to work. You don't just, hey, it broke down. Okay, we scrap it. Like, that's not a good use of money, right? So that's one thing, is having those manufacturers be around for a minute. Well, what I've heard from others is they're around for a couple of years, they either get bought out or they just dissolve because someone else came in, or the technology just, surpassed whatever they were using at that moment. So I think some utilities, others I know are going for it, but I think a lot of like your mainstream, or majority of like the middle of the road utilities, they're just not willing to jump in yet, because they're like, well, nothing's really kind of leveled out. They're still kind of on an incline, technology wise, and improving. I don't know, Andrew, have you heard other things since you kind of interface with a lot of other utilities?
Yeah, one of the things I've seen on that kind of same line of thinking is one of the biggest challenges I've seen, at least on the technical side, is inverters, right? All these storage systems are typically DC systems, battery banks and whatnot, and
And just for,
converting to
could you
convert.
say what DC is? Can you elaborate what
Oh,
DC
sorry,
is?
DC
Yeah.
is in direct current electricity. So there's two kind of like forms of electricity, if you will: direct current and alternating current. So on the electrical grid, and if you go back into the history books as to why, Edison was kind of the direct current guy, and Tesla and Westinghouse were the AC guys. And one of the reasons why AC kind of won the battle of electricity, if you will, is because of how easy it is to transmit alternating current versus direct current. Edison, built one of the first power plants, but you realize that if you have to have some really giant conductors or wires to transmit effectively, because of how much loss there is over a direct current line, unless you can run it at a high voltage, which is challenging to do, especially in that day and age. But Tesla and Westinghouse and some of the innovators at that time created what's called the transformer, which a lot of us kind of understand that term. And essentially what a transformer does at its core is it transmits electricity, or converts it from one voltage level to another relatively efficiently and easily. And when you transmit things at higher voltages, you can reduce the amount of current and get the same power output than you would if you were at a lower voltage. So that's why when you look outside and you see these giant poles high in the air, the reason why they're high in the air is because they're running electricity at very high voltages, typically above 100,000 volts what's called phase to phase between the two wires. So that's why, right? Because, as we all pretty much know, I mean, or most of us know, is most power plants aren't sitting next to your house typically, right? So, you have to produce that electricity and transmit it sometimes across hundreds of miles to the load or to the consumer, right? So doing that efficiently is very important. And that's why AC electricity is the most common in terms of most of the grid. But you have to understand, though, especially in today's day and age, a lot of technology, like a lot of your batteries and your cell phone and your electronics, they run on DC, direct current. So funny enough, we spend all this time converting everything to AC, and a lot of the electricity is produced in AC, but then at the very end of the line, when you plug it into the wall and you have your little charger, it actually converts it to DC. Funny enough, if you look at it, that's how most electricity is consumed now. But anyways, so say, what was my point about the DC and AC? Oh yeah, so most energy storage systems, right? So they're running off of DC, right? So they're a battery bank, so which is a direct current, typically a direct current device. But when it interfaces with the grid, it has to convert to AC, just like pretty much any generating source. And what that device is called an inverter when it converts from DC to AC. One of the biggest challenges in today's day and age is, unlike traditional power plants that kind of run off of a magnetic physics type principle, all these inverters are run off of solid, like electronics, and they're controlled by whoever the vendor is that created them, right? And they can do a lot of great things with these inverters. I mean, basically they're controlled by a program, right? Essentially. But one of the challenges with that is, from what I've been told, I don't have a ton of experience with it, but some of the folks in our company do work on a lot of these projects with inverters. Inverters can work very differently between vendors. Heck, even firmware updates in some of these inverters can work very differently. And from a utility perspective, that can be very challenging or frustrating because they want something to work consistently. right, and work the same way. But if, I've been told by some folks that have, again, more experience, that you have to be really careful if a vendor says, hey, I want to change the firmware in a device. Typically that seems pretty, harmless, but they say be very careful, because if you've tested an inverter with specific specifications and specific operating conditions, but then you change the firmware, it can completely change how that inverter exactly works, which can be challenging, right? Because then you have to retest it all. I don't know the full steps of how they test it, but that is a challenge, right? Like Brandon said, with vendors changing and potentially going out of business, also the operating characteristics are very different. The principles are very different than traditional power plants, like a coal generating or a gas generating plant that runs basically off of physics. So that's another big challenge compared to the traditional grid.
Explain what firmware means, because not everybody is technologically advanced.
So think of firmware kind of like an update on your cell phone, right? So essentially, if you have an update that's required, and again, with these inverters, it not necessarily, again, it depends on the vendor and the manufacturer if they recommend one or not. They're not necessarily like your cell phone that requires patches, but in some cases they do recommend an update similar to like a cell phone update. But if you do, kind of similar to your iPhone, it can change. It doesn't necessarily completely change how the phone works, but it definitely adds features. From a consumer perspective, the phone is not an issue, but when it's something operating part of the grid and you want it to work consistently, that can be a challenge, right?
Yeah. So we kind of actually ran into a few of the other questions. So let me try to organize this in my head for a moment. I guess so. That'd be the big challenge with solar. Is what you're saying is basically like we want this battery technology to kind of update more so that we can actually use these more flexible and constantly changing technologies when it comes to solar and stuff as energy provision or hydro output. So when we're kind of thinking about how would that work? I know I've read articles. I think a lot of people who've tried to invest in the space, especially if they're trying to invest in EV vehicles, they've read a ton about these giant batteries the size of buses and applying that to infrastructure, building that near a city. And then we're talking about, all the little delicate complexities of incorporating that into a system and everything correlating to that. Do you think, when we're kind of incorporating also the pace at which the government wants us to move to this clean energy, and then the disconnect when I talk to you and you say, well, we kind of want these technologies to keep up with us, that and all these regulating bodies that we also deal with also have all these regulations and procedures. Everything moves slowly. There's this company might make this change and this company might not even exist anymore. So, that when it comes to that complexity, how does that fit into your day to day? Does that become a frustrating thing, or is it more of an exciting thing of like, well, at least we got these batteries the size of buses now? Or is this still something that is a decade away and just kind of still in a sci-fi state of a conceptual idea? What is your, pick anything out of that if it interests you. Who would like to hop in?
I can speak on the process of essentially renewable energy in general. So I mean, the idea is that whether it's sun or wind, idea is it's going to produce a bit of power. It's going to be connected to the grid, and it's going to help support the grid. Well, unfortunately, there are times when it kind of destabilizes the grid, right? And there are times when we have to literally cut it off, right? We have to open up a switch, and even though it can still produce power, it can still the turbine that's spinning with the wind turbine, it can keep spinning, but we're not going to take the power because it might be just destabilizing the grid, or something else is going on at that time. So as much as it seems like it's just as simple as you just plug and play and we're done, it's not really that way. So I've talked to some transmission operators where they're saying that because of I think at the time this was a wind generation, where they've had 20 kV or 20 kilovolts drop from the system in 15 minutes, which is pretty drastic. It's a very fast drop based on whether the wind was blowing or not. So that's not something you want in your grid. You want your system to be balanced and you want it to be consistent. So that's the other thing about these EV, or not EV, but the renewable sources, that they're not very stable.
Yeah, so that's
So
that's actually something I would like to double click on. So that's the battery. This bus size battery near the city not only serves the purpose of like what my assumption would be, and I think what lots of people would assume is like a backup. Like if the grid goes down because there's inconsistent energy, this would provide that consistent energy. But I think something that might be missing there from the general population's knowledge is sometimes there's energy being output, and you need somewhere to just stick it.
correct.
Is that what I'm
That's
picking? Yeah.
that's essentially the goal here is because you can't always have it on, and we don't want to just waste energy and not produce it and capture it. So the idea is to have a battery source, some sort of battery, whether it's like our typical lithium ion or something of that sort, some technology similar, or to go into like the hydrogen world and use that as kind of like a battery in that you're storing hydrogen gas to then be used, burned, and turn into energy later down the road. But that's kind of essentially the goal, and the battery technology just isn't there yet. So
Mm.
that's the big thing here is to produce power, somehow keep it, and then expand it when we need to, because obviously the sun doesn't always shine and the wind doesn't always blow, right? But when we
Mm-hmm.
have coal or natural gas or any of those other or nuclear energy, we can burn that or however we want to expand that energy. We can use that pretty much at any day, all day, every day, because we can get that sort of energy source and just continuously feed it, right? And that's what's so nice about it is that it's very reliable and it keeps the grid stable, right? Because we know exactly how much to buy of whatever the source is, and we can make sure that it just keeps going, keeps flowing. So and it's relatively cheap. So that's why
No.
coal and things of that nature are very good, because it makes it very easy for us to have a very reliable sense of lifestyle, right? We don't have rolling blackouts generally, unless there's a storm going through or something going on. But generally, we don't experience that. Whereas you go to some of these islands and more remote places where they just don't have that capability. They're used to having just rolling blackouts. Like every so often, the lights just go off. You're just going to have to deal with it. And that's why renewable energy can be a bit of a challenge, because if we just turned everything off and just only ran on renewable energy, that could potentially happen. Where it's like, hey, we're not getting enough generation. We're going to have to cut the load. We have to load shed,
Yeah.
and that's what happens. And that's I don't think majority of the people, at least in America and whatnot, are going to want to deal with that. We're pretty used to having all of our lights on and our TVs on and everything on. We're not really used to just like, I guess I'm going to have to turn this off now. So
Yep.
that's kind of the big thing here, right?
Yeah.
Is how is that all going to work?
Yeah, and that sounds like also, I'm not sure if either of you'd be able to speak to it but the extra complexities and the fact that when you're dealing with oil and coal, you're dealing with a legacy company that's probably existed for 50, 60, a century, or this battery company, as you said earlier, which may not exist tomorrow. So, yeah, so, or just popped up. And I think a lot of even just investors can recognize that with all the new tickers and SPAC products, and which is interesting. Is there anything you'd like to add to that as well, Andrew? Anything that piqued your
Yeah.
interest?
I mean, I
Yeah.
can go really deep into how technical we want to get, but one thing I'll point out, because again, I'm a relay guy, so
Yeah.
we'll throw this out there, right? One of the other big challenges to renewables in terms of stability is, basically to give a quick, like, high level of what a relay does, right? The company that I work for and what we produce is what a relay does, similar to in your house, right? If you have a short circuit, meaning like a fault, something happens in your house, like a wire touches, the wrong something it shouldn't touch, it creates what's called a short circuit. A lot of energy flows through that short circuit, and in your house, it causes a circuit breaker to trip or a fuse to blow, right? Well, when you're in the transmission grid and you have hundreds of miles of transmission lines or more complex equipment, circuit breakers at that level aren't smart enough to be able to trip themselves or open to isolate that huge amount of energy, right? So what a relay does is it basically monitors whatever piece of equipment, a transmission line, a transformer, generator, whatever. And if it detects a disturbance or a problem like a short circuit, we call it a fault, but short circuit fault, whatever, um, you know, basically we tell the circuit breaker to open, to trip, to open and isolate that energy to prevent, more damage, fires, and what have you. Well, that being said, traditional generators, coal-fired, gas generators, hydro dams, they're rotating machines, right? So they're literally rotating at sometimes thousands of RPM. So they're very they have a lot of inertia. So they have a physically they're moving, right? Well, when you're talking about a solar panel, for example, it's not moving, right? It's static. It has it's zero inertia, right? So to simulate that inertia, there are devices that we can put on the grid to kind of simulate to an extent that amount of inertia. The reason why the inertia is important is because when you do have a disturbance, like one of those short circuits, and you do have a giant grid with all these generators in parallel, essentially, it is relatively resilient to short circuits as long as you isolate them fast enough. I mean, there is what's usually called a critical clearing or stability time, but that's usually that amount of time is sufficient for these generators to basically ride through those problems, so they don't shut off completely, right? But these Solar and other alternative energy sources are not nearly as resilient because they don't have that same physical inertia. So that being said, it creates challenges when you have disturbances. Like, for example, you can read different articles of and again, there's different, like anything. That's the other challenge, is there's vintages, and if you start talking about wind power, there's different types of wind turbines. They're not all built the same, so they can work physically very different compared to a coal-fired plant. For the most part, it's going to run the same. It's, again, because it's been running the same way for the last 50, 60, 70 years. It's going to run this. Most coal plants are going to run in the same way. Sure, their boilers and some other pieces of their mechanical side may be slightly different, but the electrical part is basically all the same. But that being said, it creates certain challenges with these renewable sources. And you can, like what I was going to say, is you can read some articles of how, especially older solar plants that I think have become more resilient. And again, some of the protective relay and things they put on them, the control schemes are advancing. But you can read stories of how a relatively large, in terms of megawatts, so thousands of watts, millions of watts worth of energy being produced by relatively large solar plants, like in Arizona and some places in the Southwest, when they've had disturbances on the transmission grid, disturbances they really shouldn't operate for, they completely disconnect from the grid. Megawatts, millions of watts of energy just getting shut off instantaneously because of a disturbance that really it shouldn't have operated for. Right. So you can read plenty of stories of that, obviously, like I said, there's been learning curves, from a lot of folks in a lot of these companies. But the point is that there's a lot of challenges that we have to overcome. And some of these regulations are helping fix that, but yeah, it's very challenging. In terms of when I've done, regulatory studies too, like when you look at some of these control schemes of some of these plants, it's a lot more complicated, and not only complicated from the perspective of, just the scheme itself, it's the fact that you almost have to talk to the vendor itself to understand how it works, compared to, sure, there's complexities with any generating plant, but in general, the physics is the same, like I keep saying, with the traditional conventional plants. So those are all different challenges.
Yeah, do you see that kind of typically when you with any a new industry on the come up, there seems to be some consolidation in the innovations or some sort of standard that gets set. Do you see any development of that, or is this still kind of like the Wild West where they do it this way, they do it this way, or is it already kind of like, well, you have these three major, your AT&T Sprint that typically,
I see what you're saying.
yeah.
That's a good question. I've been told, and I'm not as familiar because I don't do as much work in Europe, but I've been told in Germany and some other European countries have become a lot more. They have a better set of standards that they tell different vendors how they want their inverters for. Because inverter is one of the key pieces, right?
Right.
Like I keep saying, but they have more of a better standard, from what I've been told, of how they want their inverters to work and how they want them to operate under these abnormal conditions. Because that's working normally is great, but during abnormal conditions is really when you want to know. Because when you have a storm pass through, you want to know what's going to happen, right?
Right.
Just as important as quote unquote normal, good times. So I've been told in Europe they have a better standard. In the U.S., I think we're moving along. We have a couple different entities. California has its own specific set of rules, and I know nationally, I don't think we have quite enough standardization, if you will. From my understanding, is it is not exactly the Wild West, but it's not quite there from what I've been told in terms of like standardization of how inverters should work. For example, like that whole inverter or that firmware problem I mentioned earlier, that from my understanding hasn't been fixed. And I think going forward, eventually, probably 5-10 years from now, I'd like to think that that will become a lot more standardized, so that for example, one of the things that we run into is how to model our electrical systems. Because one of the things that I do in terms of studies is, when we set our protective relay, and we like to see, what available fault short circuit currents are available for different types of events. So modeling that is just as important to understand how, basically predict how things are going to react. And if you don't have a good model of the system, right, it's challenging to understand how to program them properly, right? So again, going back to traditional generators, it's relatively simple because the physics is pretty simple, but these conventional generators, even just getting to model them properly can be challenging. But it's getting there, it's getting better, but it's just realizing that it's not as simple as as traditional generators have been in the past. And one of the other big things too is in distribution systems, normally power traditionally has flown in one direction, right? So you have a generating source, a transmission source, and then what's called a distribution source, where it's basically all your neighborhoods and your different businesses and loads, industrial plants, what have you. But now with folks putting all kinds of solar and other types of sources on their rooftops, right, it can also present challenges to traditional distribution grids that weren't really historically designed for basically for every house to be its own little power plant. So inverters, residential and even some commercial inverters are supposed to be designed to be able to shut off when they detect the loss of the utility source, but it is challenging. That's one other aspect from a safety perspective, right, is making sure that, if a lineman works on a distribution line, normally he just has to go to his nearest substation and make sure things are all disconnected. But now he may have to go to all these individual homes and physically go to disconnect all the different sources to make sure that he's safe, right, before he can actually start doing any work on a line. So there's a lot of challenges that are presented.
And a source meaning something that generates and can contribute power to something, as opposed to just a load which is consuming power. That's what he means by that.
Yeah.
The thing. In a distribution sense, you're used to everyone as a load, right? I'm eating all this power. No one's producing. But now that you have people that are installing generally just solar panels on their house and stuff that can produce power, so then if there is, like Andrew was mentioning earlier, a fault, or let's say a tree falls on a distribution line, and the power is now flowing between it and going to ground, which makes it dangerous, right? Instead of it just being like, oh, we can just isolate, well, now you have another source that could be contributing to it, which is that solar panel or that whatever. So it makes it a little bit more challenging, as opposed to, just cut the thing at the beginning of the source and it'll cut everything off. Well, no, not anymore. So it makes things a little bit more challenging, and some utilities aren't a big fan of people having their own individual solar panels, just because it is a little bit more of a headache.
Yeah, all I can think of is there was a very, very popular a podcast from the All In podcast. This podcast features 4 big name billionaire investors, and they spent about 40 minutes talking about how they could solve basically all the clean energy issues if the government spend all the money to build everyone their own solar panels on their house, that all problems would just disappear. And that's all it would take. They only priced out how much for the exact solar panel. And so they said, see how cheap it would be to solve this. And now even just hearing this, it's like, that's so much fantasy involved in that. So, even the extra complexity that I didn't know of, having to go to each house and to do any operational work in the area, to have to disconnect each house for the safety of it. And I imagine that there's probably some sort of like, which company made this solar power, and how much energy is this panel making opposed to this one, or although I think there are some limitations in even the output for that. And actually that's another question. How much of those challenges, when it's a solar power especially, how much of those challenges are due to the actual amount of power output that those panels can make? Or even we can throw gas into it as well. These alternative clean energies. Actually, the EU just recently officially made gas a clean energy source, which it previously wasn't listed as such. So when we're comparing the output that these make, not just the stability, we kind of covered the stability and the different complexities in that, but when it comes to pure output, like, is it something in the future the technology can keep up? Is that doable? Does it seem like a physics problem that can't be solved and we're trying, playing in fantasy a little bit here? Or is it just going to take some more time for the innovation? Or is it already here and it's just implementing it is such a hassle that just takes time to get all, these are very delicate systems, as anyone listening is probably caught up on right now. But is that something, who would like to tackle that one? I know that was a big question.
So my perspective in terms of energy density between like gas and solar or renewables in general, I mean, renewables take a lot more area to make the same amount of power in general, right? So if you're in areas that have a lot of open space to put a ton of panels, because my understanding, and again, I haven't done research in solar panels in a long time. I mean, back in school, we talked about how, from my understanding, at least at that time, and again, it's been a little bit of time, but they were relatively at their upper limit of efficiency. So from my understanding, unless they start coming out with newer technology of what to put in these particular solar panels, they've kind of reached their upper limit of efficiency, and it's not very high. If I remember, it's 20-25% efficient. I mean, it's quote unquote free. It's coming from the sun. You don't have to have any other source to generate it, but the actual full production isn't extremely efficient. Maybe it's a little higher now. Maybe it's 30%, but natural gas, on the other hand, just for example, I've been to several plants. They have some that are called combined cycle facilities where they burn natural gas, they generate a lot of heat, and they take, and in some configurations, they take that excess heat and they kind of run it to create steam, to create a steam generator as well. So they kind of like do a 2-on-1, 2 gas to 1 steam turbine type configuration. So it's definitely a lot more efficient to do that because you're not wasting a bunch of heat that you generate naturally from the natural gas process. So, and in those types of units, for example, that don't take up very much room at all, they can run several hundred megawatts, no problem, right? Or 1,000 megawatts. But, again, solar panels, if I remember correctly, one of the local coal, and this is going to coal a little bit, which I know is a little off topic, but just to put it in a little bit of perspective, one of the coal plants we have in Missouri, one of the biggest actually in the country now that's still in operation. I remember going to that facility years ago, and one of the folks telling me that, to produce in this case, a wind farm that would be able to produce the same amount as that one facility would take, I forget, like 1,000 acres, like this entire county full of wind turbines to produce the same amount of power. And that would be assuming that the wind was blowing all the time, right? Whereas this coal input is relatively consistent because they have coal trains going back and forth all the time. My perspective is, I think hopefully over time these renewables will gain a little bit of steam, and hopefully one of the biggest tackling issues that we talked about was storage, because electricity is consumed as soon as it's produced. It's moving at the speed of light, right? Unless you have an efficient way for it to be stored, it's being used as soon as it's made. That's what's kind of incredible about electricity. A lot of people don't really realize it's constantly moving at the speed of light. So unless you have really good ways to store it, especially on days where you have excess sun, if you had a ton of solar everywhere, it's going to be a challenge. One other term you may have heard that's very hot term these days is microgrid. You probably heard that term, I'm sure. And the intention or the idea of a microgrid is to, instead of having one major grids, like we mentioned earlier, there's 3 major grids in North America: the Eastern Interconnect, Western Interconnect, and then Texas, because they have their own, of course. Instead of having these giant grids with all these, these large transmission lines in between, if you had more localized generation with a lot of solar panels or a lot of little wind turbines in localized areas, you wouldn't necessarily need a large, set of high voltage transmission lines to transmit electricity over hundreds of miles. But I personally see obviously a lot of challenges with that. I mean, the most common microgrids I see these days, quote unquote microgrids, are really where you see a combination of sources, like on, university campuses or some specific industrial facilities where they have a combination of, solar panels, maybe some wind turbines, not a whole wind farm, but, some turbines, maybe a gas generator, and then of course your traditional utility interconnect. That's kind of what the latest quote unquote microgrid looks like. I've not heard, especially in the US, of anywhere, areas where they've kind of completely gotten away from traditional distribution systems where they're connected to a high voltage transmission grid. Of course, it can happen in the future. It's possible, but I definitely foresee challenges and a lot of upfront cost to developing a really good infrastructure design to, be robust enough to produce reliable electricity for a relatively large group of folks. But anyways, I mean, that's kind of, I think that's what, when you hear the term microgrid, that's where we're going in terms of having more localized generation that could be more efficient. But we'll see if that actually takes off.
Yeah, so I'm not familiar with that. So with the microgrid concept, but did you want to add something to that, Brandon?
Yeah,
I was
please.
just going to say one thing to help others that aren't as familiar in the power world. How is power made, right? Excluding solar panels, because that's a whole other process, but pretty much every other process is just about the same way. You're spinning a turbine uh, of some sort, right? Some sort of generation. You're spinning it so that it creates power, right? And the means of how you spin it is of the question, right? Well, in a hydro dam, you have water literally falling and going through it, and essentially it's creating pressure through gravity. So it's going from a big tube to a smaller tube and a smaller tube. So it creates that pressure, so it can has more of a push or a force to exert on these turbines, so they can spin and then create power and all that good stuff. And the beauty of that is that if you have a big pool of water and you have that gravity difference, then you can kind of control how fast the water is going to go and how consistently you can use it and all that good stuff. Oh, there's too much water because it rained. Okay, cool. We're just going to have that go over the, some of the escape portions and all that good jazz. But everything else generally, whether it's gas, coal, or even nuclear reactors, it's all about the same thing. What's happening is you're taking water, you're heating it up from some source, whether you're burning gas, you weren't burning coal, or you're having a nuclear fission reaction, which is creating heat. Same thing. You're heating it up, you're boiling this water, turning it to steam, and that steam, again, smaller and smaller pipes that are making that pressure, force, high pressure, and it's pushing this turbine, creating energy. And same thing, wind turbines, instead of having water that's being turned into steam, it's just having the natural wind spin it. Same idea. But that's essentially all that's happening here. Rather, it's what really the major ones, right? Nuclear and coal and natural gas. It's really just about what's burning, right, to turn in water to steam. So just to kind of give people kind of a quick idea of that. Whereas solar is a little bit different. It's photovoltaic and it's a completely different process. It doesn't create alternating current energy. It actually creates direct current voltage. So it's a little bit different, but we don't have to get into that. It's more of a chemical reaction as to what's going on there. But I just thought it might be useful for people to understand really what's the question. And the question is, how do we get this device to spin, right?
So when it comes to gas, what are there different gases that were used? Are there different challenges when it comes to using gas energy in particular? I've read lots of different futuristic articles, but honestly, my knowledge is probably just as vacant as the average person. So if you could actually just speak to gas in specific a little bit more, I think that'd be really informative as well. Especially, with being such a major topic in the geopolitical environment with what's going on in Germany, where they have this huge vacancy now that they have to try and fill from other countries and neighboring the area. So what are the complexities that go with that, and even with transporting it through the big pipelines, if you want to speak to that? Mostly if you want to stick to production and more pertaining to your expertise.
Sure. Yeah. In my experience, from what I've seen and from what others have told me, we use quite a bit of natural gas in the U.S. from what I've seen. I believe even more than coal and nuclear. And Andrew, you can tell me if I'm wrong. I think we looked into that earlier. But we're using actually natural gas more than anything, and it's a pretty good source. And I believe I recall research a while back where the only reason why we had a big uptick in coal plants was that there was like some articles in the late 60s and 70s talking about how gas was not the way to go. And I don't remember exactly what they were trying to say, but it was the big push for coal. And that's why a lot of coal plants that got started up in the 70s, like a big push of them. So almost all of them, I shouldn't say all of them, but a good amount of them have been a vintage of like 1970s in that ballpark. And kind of a similar thing with the nuclear plants. A lot of them are kind of 80s, 90s kind of thing, or late 70s kind of thing. But natural gas, from my understanding, is very good, very clean, and nothing really to have a major concern with. I'm sure someone can come up with a concern, but from my understanding, it's pretty good. I don't know, Andrew, you can touch on that if you have a better grip on it.
Well, yeah.
Oh, go ahead. Sorry, Josh.
Oh, sorry. I was just gonna add. Is it hydrogen? Is the gas that we're mostly using? Is there different experiments with using different gases to?
My understanding, I don't know of anyone using hydrogen right now. I'm sure there's probably someone experimenting, but
Okay.
right now it's all natural gas. I've heard of other utilities considering doing either a mix of natural gas with hydrogen,
Okay.
but I don't believe that's happened as of yet. But again, someone might be doing it. Since the infrastructure already exists, with the pipelines and whatnot for gas. So I believe that's something that they're going to consider doing. But again, it comes with a challenge because natural gas and hydrogen are not the same thing. You can't just cut one with the other and it's just going to work out the exact same way. So
Yeah.
there's some nuances there, and I'm not a gas engineer. I can't, completely
Yeah.
talk to you about how the combustion is going to work and how that's going to affect, settings and ratings and so on and so forth. I
Okay.
just know that I know that people are going to try it.
Yeah. Appreciate the input. Yeah, Andrew, you wanted to
Yeah,
hop in?
I have read some articles about some, Microsoft and some other big names trying out hydrogen and some, but on a utility scale, I personally haven't heard. I know lots of folks have their opinion about how they could potentially make hydrogen work, but like you said, the infrastructure right now, from my understanding, definitely not a gas expert myself, but is definitely natural gas pipelines, right? But they have their own energy, their own aging infrastructure issues as well. A lot of them, like Brandon was saying, have been designed and utilized for a long period of time, so they have their own aging issues. But yeah, there are websites like there's the U.S. Energy Information Administration, the EIA, that does talk about kind of the latest statistics of our consumption and our biggest generation by energy source. And natural gas as of 2019 was about 38%. Took up about not quite half, almost 40% there of our usage in terms of what we used to generate electricity. Renewables was almost 18% or so. But coal and natural gas together were more than 50, like 60% or so of our leading uses. But again, that was 2019. I know administrations have changed, and I think the coal percentage has definitely probably gone down a little bit since then. Nuclear was almost at about 20%. But yeah, I mean, I personally have seen natural gas can be relatively reliable. I haven't heard of a lot of issues. Obviously, like we talked about earlier with Texas, and then reliability issues if things aren't designed, pipelines aren't designed very properly, it can present its own issues. But beyond that, I haven't seen a lot of concerns with using it.
Okay.
And to be fair, when we say designed properly, it's not that they're not designed properly, it's that they're not designed for a type of temperature or weather that they get once every 100 years or so. We're not going to discredit the people of Texas and how they design their system. It works, obviously. It's just they're not they're not designing their grid so that they have Texas or Alaska type temperatures every so often, right? And so everything's about how much does it cost, because you have to weatherize it, right, to beef it up so that it can handle something that's colder temperature or this, that, and the other. Just the same way that utilities in Missouri do not design their control houses for the same standards that they need down in Florida, right, for the winds and stuff like that. So everything's just a little bit different because of the particular climate that you're in.
That's
So
That's a good point. I mean, you're right. It's all relative. Like, for example, one interesting thing, because I recently went to Alaska, talk about Alaska. And I had never seen this before. It was pretty interesting. Their substations, for example, were all put on like an 8-foot platform. Nothing was ground level. And I asked, they called them a skid, but essentially this big metal structure that was, like I said, 8 foot off the ground. And I've never seen that before. Pretty much every substation I've seen here in the continental U.S. is everything's ground level with, a bunch of rock and other things for insulating. But I've never seen a substation up in the air intentionally. And they said, well, it's because the ground freezes and it moves and it's just not stable enough for them to be able to put a flat substation at ground level, which I had never heard of before. So that was actually really an interesting experience. But that is a fair point. I mean, it's all relative to cost and probability. And if you're living in an area that's that far south, I mean, it was just a terrible event, but it's not something that necessarily going to spend billions of dollars to fix because it's just statistically not very likely to happen again the same way. But it could. I mean, personally, I think it could happen again.
Yeah, well, especially with the global environment changing and stuff, and hitting new records every year. Yeah, that is very interesting. I guess is a good point to kind of also transition to my favorite form of nuclear energy. And for people who've been following the YouTube and the social medias for Nobel Trading, I'm a big fan of nuclear. I love nuclear, and I actually have done some research, but I'd love to hear from you, the actual experts, like where does nuclear play into your viewpoint? Like, we've barely even touched on it yet. Most of the clean energy that is produced in the whole world comes mostly from nuclear, overwhelmingly. This is 60% from 2020 data that I was looking at. So how does that factor into into your expertise? What do you think about nuclear energy, just holistically?
In my opinion, ever since school, we've always been a big fan of nuclear energy, just based off of the benefits. I mean, we're used to seeing. I remember someone had this little diagram or whatever, where you see this little pellet, like about this size, barely, maybe not even an inch long, could power like a home, not a home, like a whole town for like a month. And like this tiny little piece could to do all of that, and you're like, oh my gosh, like how great is that? And understanding how much uranium and all those types of sources that they're used for the fuel rods, how much there is in the world, you're like, we're set. We've got the energy, we can do it. The same thing with coal, though. We have quite a bit of coal as well in the U.S., like a lot more than you would probably expect. From people I've heard, they're like, oh, we could power just from this one coal mine, that they were referring to, at least another few hundred years just from that one alone. And it's clean and it's good and it's easy to get to, kind of thing. So we have a lot of ways of getting power. So, but nuclear especially, it's very clean, it's very good. Obviously, the biggest thing is there's that relatively small risk, that's high risk, where if something happens, like a Chernobyl or Fukushima or whatever, if that happens, that's a big concern, because then it becomes a health problem. Whereas if a coal plant blows up, yeah, it sucks, it's not good for the environment, but it's not going to generally kill the entire country, kind of thing, or many states, or whatever the situation is.
Cause
so that's why it's a little scary. But my other understanding is that nuclear reactors to build, from the idea of just talking about it to the finished product, I mean, my understanding is it's like a 30-year process. Where it's to get all of the regulation and the permits and the licensing, that's like 10 years, and then to build it is another 10 to 20 years. And someone can spend their entire career just building something, and then that's it. That's their entire career, is just building it. And they're obviously designed to last a good while, but like anything, unless you maintain it very, very well, nothing lasts 100% forever. So, and since the governments are relatively afraid of that stuff, and they're really kind of like, no new permits for nuclear energy in the U.S., from my understanding, no one's really going down that route. From what I've heard.
But they're also going down the route of coal is bad and not good for the environment, and oil is bad and not good for the environment, which leaves, when I'm kind of looking at it, especially the complexities that we talked about, it's like, okay, the nuclear seems like the best option and the best path forward. And I know you weren't nuclear engineers, or especially who would want to be a nuclear engineer, like you said, and that's a lot of the legislation and legalities around it that I've seen is your whole career would be based on one project that will probably never happen. And if it does happen, you probably won't be around to actually see it get completed, because it's going to take your entire career for it. So yeah, I mean, yeah. It's extremely difficult. Sorry, my voice is getting rough. Did you have anything that you wanted to add, Andrew, to that, or?
No, I mean, I'm basically picking back off what Brandon said. I definitely agree that the energy density is like insane, what you can really do with nuclear power. But like Brandon said, and I've experienced it a little bit, even more recently, actually working on a few projects where they're replacing some equipment out of a nuclear plant, and the amount of regulation and the amount of steps you have to take compared to a lot of other facilities it's very extreme. And the amount of paperwork, I should say, you have to do to prove that you're doing things their particular way is very, very exhausting. But I'm definitely a huge fan. I mean, I wish that, not to say I wish there was less regulation per se, but I wish it was a little bit more streamlined. I think I think nuclear plants are definitely would be a great thing for the future, especially maybe even smaller scale per se. I mean,
Yeah.
maybe it'd be easier to build smaller reactors and larger scale in terms of a lot more smaller plants and just these larger facilities. Because some of the nuke plants that I've seen, are just really large facilities. I mean, just to put it in perspective, we talked about some units that can produce a couple hundred megawatts worth of energy. Some of these are 1,000 or more, 1,200 megawatts. So they're typically very large. I mean, they can be, right, because they can produce a lot of energy. But the challenge is building new ones. And I hope that in the future that there is a bigger push, like you said, because it is a very clean way to produce energy. And it is very dense. So I hope that in the future we can produce more. But right now it's not looking so great.
Yeah. That regulation actually doesn't exist for the military, though, because we do use aircraft carriers with small nuclear reactors on them.
True.
Why they
Good
can,
point.
stay away from shore for 20 plus years without having to refuel.
That's a good
Which
point.
could you fit that into one of your microgrids? Like, could you have a little mini nuclear reactor
Oh yeah,
for a
you
whole?
absolutely could. I mean, you could probably argue that some of these, probably some of these military craft are practically microgrids. I mean, they're probably only running, like you said, just a nuclear reactor. They don't need to have solar panels or anything like that. But
Yeah.
but I would call that a microgrid because it is basically a small area that's consuming power. It has one main generating source, but probably with backup, I'm sure, with little diesel or some other. I'm not really familiar with those, craft in particular, but I'm sure that they do they do kind of run their own little grid. So I would call it a little small microgrid.
I'm sure there's some sort of regulation with them because if you've
Oh
ever
yeah.
worked with the government, and I
Yeah,
know some of us have, that there's quite a bit of paperwork and things that hoops they have to jump through. It's not as simple as one, two, three. There's definitely a lot going on,
Yeah.
but I agree. It clearly if there's a will, there's a way.
I was being a little facetious, but
I know what you mean.
with the way it's portrayed, even Elon I think has tweeted about this where he's like, I'll go eat vegetables near Hiroshima just to prove a point. Like he was
Right,
like it's safe now, it's okay, like you can
right,
recover.
sure.
Yeah, so I think we've really touched on a lot. This has gone great. I would love to kind of to exit this with just like what excites you the most in your field about the future, like what new technology or innovation really like like gets you giddy like a little kid at a candy store. Whoever would like to start. Brandon, you want to kick it off?
Yeah, sure.
Yeah.
For me, I think the thing that I've seen that's been they've been experimenting with, and it's definitely more serious now, is actually HVDC, which is high voltage direct current. So I know we mentioned earlier how direct current was not the way to go, especially back in the day, but they're starting to play with that now, and they've had that small lines. In different areas of the U.S. and I think across the world as well. But they're starting to get into that more, and I think that's pretty interesting because it kind of turns everything on its head in regards to how power is transmitted. And so for me, I think that would be interesting to learn the nuances of this, relatively old but new technology, so to speak. So for me to learn about that, how everything's going to be different, and it's just a completely new skill set of how things need to be done, I think that would be pretty exciting.
Yeah. What was that called again?
HVDC, high voltage direct current.
And that would.
So
Oh yeah.
so I'll explain real quick. Kind of. I mean, again, I don't have a ton of experience with it, but essentially the way that works, and the reason why it didn't exist 100 years ago is because effectively what you do is you have a high voltage alternating current system like we do on our big tall transmission towers. What they do is they have what's called a converting station. So power electronics now are obviously a lot different than they were when in Edison's time. So essentially what they can do now is at that high voltage alternating current that they use a transformer to get at that voltage level, they have very powerful electronics that can basically chop up that wave, that sinusoid, that alternating current waveform, and turn it into a direct current waveform with filters so that it looks relatively constant. Because that's the difference between an alternating current and a direct current. And then basically, interestingly, and I've only read a few articles about it, interestingly, they've done research, a lot of folks have done research that says when you run transmission lines over hundreds and hundreds of miles, which, you know, around here, just to put in perspective, in Missouri, Illinois, I mean, there are definitely relatively long transmission lines, maybe 100 miles, you know, maybe 200 miles, but most transmission lines that I'm dealing with are less than 100 miles long, right? But they're definitely in Canada and the East and West Coast, they're definitely portions that are several hundred miles. And there's been research that apparently they found that when you run at that voltage level, when you're talking about hundreds of thousands of volts, like 500 or 600,000 volts, 700,000 volts, when you're running at that kind of voltage level and you're running a high voltage direct current system, it actually is even more efficient because some of the losses that you see in high voltage AC, it's still obviously more efficient than low voltage, like you're talking about 100 years ago with Edison's time. But it is very interesting. There's obviously challenges in the costs associated with those converting stations, because what they typically do is they have a converting station at both ends of the line, right? So they have one that steps it up, the other that steps it down again, or converts it, I mean, at both ends from the AC to DC on both ends. But if you're running a really long transmission line, like I said, several hundred miles, it's more quote unquote efficient. There's less losses. I mean, and by the way, there actually already are commercially available, especially I think in like the East, like one or two in the East Coast and a few in the West Coast that already run high voltage direct current lines. They do already exist. There's not a lot of them in the U.S., but there are some. If you look up the transmission map, there are some HVDC lines already in service. I think they were talking about building one in the Midwest. I don't know like if it's still happening, but they're talking about building one from Kansas through Missouri, Illinois, all the way to like Ohio or something like that, because of essentially all the wind power that's very high producing in the Kansas area, and shipping that power efficiently over to the East Coast. But I don't know where it was. It's very challenging. Obviously, there's a lot of counties, a lot of places getting involved, a lot of people not wanting to build a big tower in their area. But I did hear about that. I don't know where it currently stands.
Wait, so that's just for the transportation of the power? Does that technology help with the you know, I imagine there's some loss from the battery to transport. So if they would it
Right. So
would
let's break that down real quick, just so I know it's a little different, it's a little confusing. So the way HVDC works, like you said, it's really just the conduit of how it goes from one place to the other. It's not an actual like technology and how power is created. You're still getting power any which way under the sun, whether it's, you know, solar, wind, coal, gas, nuclear, it doesn't matter. So you're starting with AC, then you have a converting station. It turns AC to DC. Then it steps it up to a very high voltage. It transmits it over a very long distance, hundreds of miles, and then it goes down to a station. It converts it back from DC now back to AC, and then it distributes it everywhere it needs to go. So it's that distance. It's in DC as opposed to AC, and so apparently it's just more cost effective. It's just more efficient and less costly to do it that way.
Yeah, the consumer would never know the difference, but the point is, you know, it's interesting that the technology didn't exist in Edison's time. If he would have been able to, you know, have a very high power electronic that could convert DC waveforms efficiently, he may have won the war between AC and DC. But even still, I mean, that whole high voltage alternating current part, you still have to get the voltage level to a high voltage, which is still done through a transformer, and then it goes to that little converting station that converts it to DC. All that's really happening through that station is it's just chopping up the waveform, turning it into a constant waveform instead of an alternating waveform that is created with AC. And then apparently there's been research that's been done that it's more efficient. If you're relatively short distances, the cost of those stations and the efficiency gain isn't enough to really be worth your while. It's just really, really long transmission lines. And some of the losses that occur at high voltage alternating currents don't occur the same way with direct current. It's an interesting phenomenon, but it's still not extremely, from at least from my experience, it's not very common, at least currently, right? Maybe in Europe, maybe in China, maybe other areas where you have really long distances, but in the U.S. it's definitely not common, but it's very, very interesting.
So does that well, you said that the consumer wouldn't know the difference, but wouldn't that should bring down costs at least in some sort of way, or be beneficial to the utility company? Is that a marginal difference really though?
Yeah, sorry, when I mean like the difference, they won't know when they turn their light on, you know, they're like, but yeah, in terms of, yes, I mean, in terms of like capital costs and things like that, you're absolutely right. I mean, I haven't been involved in any project where, you know, where they kind of discuss the costs of what it would take to build, you know, high voltage alternating current line versus, you know, putting this type of HVDC system. But there has to be cost advantages, otherwise they wouldn't do it, right?
Yeah,
But
you
I don't know what exactly, like how much advantage there is, but and like again, the ROI and the long-term investment, how long this because most transmission lines, I mean, they're going to be in service for 50, 60 years. I mean, sure, they require maintenance and other, perspectives, but my biggest thing is how to protect the dang thing, right? Because again, my mind goes to how is this protected when there's a short circuit, when there's a fault. My understanding, high level, because again, I haven't really worked on a project like that, but my understanding is these converting stations on the alternating current side can detect a disturbance and then shut themselves off. Now, I don't know the whole principle as to how sensitive and how exactly that works, but supposedly they do have their own algorithm or their own capability to limit how much current or power can flow through those converting stations so they don't get damaged, right? Because that's always where my mind goes, is the protection. How is it protected? How is it not going to get damaged? But apparently they of course have that considered. I just don't know all the specifics about it. But yes, there are definitely has to be some kind of economic advantage.
Yeah,
where they exist.
Yeah, somewhat of a silly question on my part, actually, but of course they would do it if it was cost efficient. No other reason, really.
Yeah.
Right,
exactly. Well,
it's not.
Exactly, right?
Yeah. It's not like a company is like, oh, we're just gonna have fun with this. But
well, there is some research done
yeah,
in some cases, but practically commercially, it's done for economic gain. Yeah.
And actually, I just want to kick this back because while you were talking this also, when it came to the transportation, then including the batteries, one topic I think I might have scanned over that I would have liked to have touched on was the when it comes to the battery technology and the transport. Is this a major component of transferring that energy? And when it comes to those batteries, is it the transfer of the energy that's a bigger problem, or the longevity of the use of the battery itself? And I know, is that a component? Is that a dumb question? Even we could start there.
I don't think that's a dumb question. I think it's the same argument as just electric vehicles in general, right? It's limited by the technology of the battery more than anything else, right? Because we have DC motors, we have brushless motors that are very efficient. That technology's been around for quite some time. So it's really just the technology of the battery and how long that lasts, and is it economical to do, right? Is the maintenance on that going to make sense, and is it going to last long enough for a bus company or whoever to buy it and say, this is going to be worth the money and I'm going to come out ahead, kind of thing. Like, I mean, if anyone's been to like New York and you look at their trains, they have trains that have been around since the 70s and people are still getting on them, right? 70s, 90s, and so forth. So when you think about transportation, you think about, okay, how long can this really last? Because we don't want to have to buy a brand new fleet every 10 years. You know what I mean?
Yeah.
They want to stretch their dollar as much as possible, because they're trying to make sure that everyone can get on the bus or everyone can get on the train, right? They want to keep costs as low as possible. So they have to be very careful about how much they invest and making sure that they're not going to get bit by, the electric bug, so to speak.
Yeah, and there's probably not as many complexities with recycling the steel from your train as opposed to the lithium from your battery.
I couldn't tell you in that regard. I mean, I don't know too many people that are doing it themselves. I think it's more or less you're dealing with some sort of contractor or company who specializes in that sort of thing, more so than each individual company or utility or department of whatever is actually doing it. I think they're more or less going through another party who specializes in that kind of stuff.
Oh, that's interesting. Okay, so they're not actually handling that. And Andrew,
I would imagine so.
Yeah, Andrew, you had anything? You want to add anything, or?
Yeah, I think from my understanding, I think a lot of it, especially when you're talking about EVs and other, really popular ways to use batteries, is the energy density, like how much energy can really be stored and effectively discharged, right? So, not only how fast it can charge, right? Because that's with EVs, that's the biggest question, right? I mean, when I had a Tesla here a couple years ago, one of the biggest challenges is when you want to go on a long trip. Sure, Tesla has figured out the charging stations, which of course, without it, it would be extremely challenging to go anywhere, far from home. But they figured that out. But it's still, when you're going on a long drive and you have to add another hour to your commute or more when you're going more than your range, that's not very convenient compared to what you're traditionally used to going to a gas station and spending 10 minutes or less to fill up with gas, right? So in terms of the speed of how fast you can recharge these batteries, and how dense they are in terms of how much capacity you have, meaning the EV equivalent is how many miles can you really go? Because one of the things I always caution folks if they want to get an EV, I'm a huge fan. Right? I love EVs because it's in my wheelhouse. I love electricity, but one of the things I caution them is to realize, when they hear the range, right? So they say, hey, 250 miles or 300 miles, you don't really ever get 300 miles because you never want to go to zero. Well, number one, right? You never want to go from 350 all the way to zero because it's not good for a battery to deep cycle and go, most say less than 20% of that rating, right? And ideally also on the top end, at least with lithium ion batteries, you typically don't want to sit at 100% charge because it really, over time, if you always have your car charged fully to 100%, eventually it starts to really decay its ability to actually charge that full capacity. So ideally, you don't ever really want to sit at 100%. So usually 80, 90%, and obviously with Tesla and cars, you can tell it, hey, I want you to stop charging at 80, 85%, whatever, unless you're going on a long trip and you're going to use it right away, right? So if you think about that, if you really only did 80% down to 20, you only get 60% of what that rating is really discussed, right? So you don't really ever get 300 miles, really. So you have to be careful with that and plan that properly. I mean, obviously the car, especially Tesla and these cars are really smart. They tell you when you're going on a trip, if you put in navigation, it'll tell you how far you can really go and if you're going to recharge, where you need to recharge it. It's very smart, but still recognize that before you get the vehicle, you're not going to really get that range. Now, that's why I'll be extremely excited one day when the battery technology is better, the density is better, and they're saying 500 miles or 600 miles, which I think we'll get there one day. That means realistically 400 miles, no problem, right? I mean, even if they say 600, I don't really need 600 because, traditional gas cars, decent ones these days can go 400 miles, 400 miles, let's say, right? Yeah. On a tank of gas. So when they start saying 600 miles and I'm like, okay, I can get 350, 400 miles, no problem, realistically. And also it's very temperature dependent too, right? So in the wintertime, these batteries getting cold, unless they're preheated properly, they also don't go nearly as far. They're not nearly as efficient. So there's a lot of factors.
Yeah, I think that's probably something a lot of people don't think about is the weather impact that it could have on the electrical batteries. And I think the economic thing is if we hit like $5 per gas, suddenly electric becomes more efficient. And that probably only gets better and better as the batteries get better and better.
Exactly.
More favored towards them. I have a quick question. Does that also apply to my phone? If I charge my phone to 100%, leave it at 100% in the charger all night while I'm asleep, is that actually bad for it? That's not something.
It's bad for any battery. I mean, any lithium ion battery at least, which all the phones still do. But here's the thing. Okay. A lot of phones now, or at least newer iPhones, I believe, I think they do have features that can like limit how fast they charge. And, like I think even some newer updates on my phone, they even when you plug it in, it says it won't be charged until this time. So it almost slow and trickle charges compared to I have two phones. I have an older vintage and a new vintage. The old one, the battery is shot, but it's also like 4 years old, which is sad, right? You think a battery should be, okay. Now I plug it in and it starts going down sometimes, which scares me. It says, 2019. Wait a minute, I'm plugged in. But anyways, it's still charged though, so I'm still good. But it's not good for really any battery per se. But I mean, realistically, when you're talking long or shorter term, a year or two, I mean, most folks, if you have a phone 2-3 years and then you get a new one, it's not going to really be a big deal if you do charge it 100%. But if you have a car or an EV that you want the battery to last, 10 plus years, then it starts to have an impact longer term, right? Right. And batteries, as you can imagine, I had friends that had Teslas that were older, even older than the one I had at the time. And as you can imagine, not to quote the pricing, because it's, I'm sure, very different now, but as you can imagine, the most expensive component on that Tesla or any EV is the battery, right? I mean, You're talking about a good percentage, let's just say several thousands of dollars to replace it. And the good thing about a lot of them is that they do have different, a group of cells, of battery cells that all get parallel in series together to create the full battery. So theoretically, it's not very likely that the whole battery is just going to crap out one day. I mean, it could happen, but realistically, what's more likely is individual cells can fail. So that means that it just won't be able to fully charge, which is still annoying because it means you get less range. But a lot of people don't like the fact that if they went from 250, now they can go 200, or, depending on how many cells fail. It's just not ideal. But if you replace the whole battery, it can be, that's the other big thing, right? There's not that's one of the big arguments is, sure, the Tesla, for example, has a lot less parts, which is very true compared to your traditional internal combustion engine, but like thousands of less parts. But When the parts that do fail they're still very expensive, because batteries are extremely expensive to replace on it. The motor's not cheap. I mean, it's also a luxury vehicle, and I love it. I mean, I do love Teslas. I think they're fantastic. But anything that does fail in it, from my experience when I had it, it was expensive. So just keep that in mind.
Yeah.
Right. And to keep things in perspective, to imagine, your current, gas car, to think in 10 years that you can't get the same, range out of it. Like, if you fill it up completely, you're going to get the same amount of miles out of it, most likely, right? Unless something really bad goes wrong. Generally, if you just maintain it like the manual says to do, you'll get the exact same range out of it. Whereas an electric, theoretically, your range can actually just decrease based on the battery health, and whether you did everything right or not, it can just happen, right?
And even how fast you charge it, because I read articles back when I was really into Tesla, and I heard folks that, sure, one of the big things, if you don't have a charger at your house, right, you can trickle charge it at 120 volts like your traditional house voltage, but it takes a very, very long time. Like, it's almost not practical. My home, I put a 240 volt circuit on it, so at least it's a lot better. It could take 8 to 10 hours, but overnight it's not a big deal. But I heard folks that, especially if you have an older Tesla and you're grandfathered in to get free supercharging, and you live near a supercharger, well, great, right? You can go there all the time and supercharge for free. But, again, that does take its toll on the battery. And I read articles about guys that would do that, and it really depleted their car's ability, even not even going 100% necessarily, but the supercharging is great when you're on trips, but if you do it all the time, it also can decrease the life of the battery. And I heard guys that had issues with being able to charge it to 100%, even after having it for 5 or 6 years, because all they did was supercharge, and they stressed that battery out a lot by putting a lot of amps through it really quickly, and it just wouldn't charge fully after. And they had to either replace cells or do what they had to do. But there's a lot of considerations, a lot of aspects that you don't think about compared to just filling your car with gas. I'm obviously a huge fan of electric cars, but it's just things to consider.
Yeah, especially as more and more people start to get electric, especially right now with gas prices, probably only going to continue to go up with all the pressures in the environment. That's really informative. Well, gentlemen, I think we're gonna call it there. I've kept you both long enough. I appreciate your time. Thank you so much. And we'll call it here at the end of the podcast. So yeah, I'm gonna stop the recording right there.